persuasive lead. And then she worked for several years for a couple of pharma companies, GlaxoSmithKline and AstraZeneca, developing workflows to identify impurities using mass spec. So a long tradition of using mass spec in various applications. She then moved to Bruker, where she took the role of product manager for the new timsTOF series. And she's currently the global business unit manager for Metabolomics and Lipidomics. And so she's going to be talking about something that should interest all of us, the fountain of youth, 4D-Lipidomics tutorial, searching for the fountain of youth. Take it away.
Thank you very much for the introduction. All right, I'm just gonna share my screen. Oops. So can you see that okay?
Yep.
Okay, perfect. So thank you, everyone. My name's Lucy Woods. I'm based at the moment in the UK. So thank you very much for including me in the agenda. And I've put together a couple of slides in which I show you how we annotate lipids to the highest confidence level and how we employ ion mobility spectrometry and high resolution mass resolving platforms so that we get high confidence lipidomics results. So for the typical lipidomics annotation focused on untargeted profiling, we have we first of all have the data acquisition, followed by processing and annotation, followed by the results, processing of the results so that we're able to annotate different lipid classes. And then we have an additional step so that we can confirm the different lipid classes which are present within our sample, which then leads us to this higher confidence lipid identification. And all of the work that has been developed as part of our workflow has been done by carefully looking at the reporting standard from the lipid maps and from the Lipidomics Standard Initiative to make sure that there's a uniformity in the way in which lipid data is presented. Now, our workflow focuses mainly on LC-MS data sets. You're also able to use this workflow for MALDI imaging of different metabolites and lipids. And to a lesser extent, there's also a shotgun lipidomics workflow. However, we prefer to use the LC-MS-based approach so that we can add to this high confidence lipid annotation by utilizing retention times from either Hillick or reverse phase chromatography, as well as using high resolution, so exact masses, and utilizing isotopic pattern and matching of MS-MS spectra. And we want to combine as many of these as much of this data or as many of these dimensions as possible, so that we can, so that we're able to validate our data and report this accurate lipid annotation. And the way that we do this is through a processing pipeline, which is based on our timsTOF platform. And then we have a series of ways in which we process the data before we annotate it. So if we look at the processing steps, so the actual, this is comprised of the peak picking. So we have a retention time alignment, which is followed by a deconvolution of the data where we de-adduct it and we make sure that every single lipid is represented as a single annotation, despite the fact that multiple different peaks, so multiple different adducts and different losses can all lead to signals which are evidently just from the same lipid class. So we use what's known as a rule-based annotation, and this uses a series of rules of looking at these different adducts and fragments so that we can assign a different lipid class. And we also use this aspect of CCS, which stands for collisional cross-section, which is where we utilize the mobility dimension to further characterize the lipid. And we do this on timsTOF Pro platform. And I'm going to explain to you a little bit about how this technology works. Now this source that we use on the timsTOF Pro is a new source, which is a heated electrospray source, which is particularly useful for the annotation of lipids. So we find that for lipids, and particularly in negative mode, we see a boost in the number of lipids and also the signal of the lipid species. So we can really increase the limit of detection. So this plot on the left-hand side here, this shows you, not sure if you can see my mouse, but I can't bring up the pointer at the moment. But the figure on the left-hand side shows you where different concentrations of the SRM 1950 plasma extract was analyzed on the timsTOF Pro platform with this new HESI source. And with the HESI source, we're able to see, if you look at the red bars, then this shows you the number of lipid species that can be annotated when compared with the standard source, which is shown in blue. And you can also see an example of the spectrum over on the right hand side here. So this is the chromatographic peak, where you can see that for a single lipid species, so for the LPE24, you get around a 5-fold boost in the peak intensity when we use this new ion source. And I mentioned before that we utilize trap time ability spectrometry. And with this trap time ability spectrometry, what we're doing is we're separating ions which have different shapes as well as different masses. So in this schematic here, you'll see there's the flat rectangle represents a piece of paper, which has then been folded up into a ball. And if you took these two pieces of paper and dropped them to the floor, then you would see that they take a different amount of time in order to reach the floor. And this is because they each have different mobilities. And this is based on the different shape or the different collisional cross sections of these two different, in this case, it would be two different lipid ions. And so this is the principle that we use to separate out these isomeric and isobaric compounds, in which in lipidomics you experience a number of different co-eluting compounds which have a very similar mass, but they do have these different collisional cross sections. And one of this is the diagram that explains how we're actually using this in the mass spectrometer. So in this second portion here, labeled as the TIMS tunnel 2, is where the ion mobility separation takes place. And then these ions can then be analyzed using a quadrupole time of flight instrument. So the effect that we see of this is that we separate out all of our ions using, or all of our lipid structures using an additional dimension. So across the x-axis here, we have mass to charge. And on the y-axis, we have the mobility. And each of these ions are separated by both the mass to charge and their mobility. So these two red ions in the middle, they have very similar masses, but different mobilities. And we're thus able to separate them out and acquire MSMS spectra for each of these different isobaric lipids. And the next step of the experiment is to acquire MSMS data. And what we do when we utilize PASSIV is we acquire 10 times more MSMS spectra. So you can see that we run a series of MSMS scans. And for each of these ions, the fragment ions and the precursor, they have the same mobility. So we're able to use computational methods to assign the fragment ions to the precursors. And this is one of the main ways in which we speed up the analysis so that we're able to acquire MS1 and MS2 data in a single run. And we're also able to acquire MSMS spectra for each lipid species. So if we look at what the raw data looks like, then this is an example again of the SRM 1950 plasma extract. And the chromatogram shown on the bottom here was acquired for a 5-minute reverse phase LCMS run. And on the top, what you can see from the heat map is you can see the retention time on the x-axis. And on the y-axis, you can see the different mass to charge signals. And every time you see one of these red diamonds is when an MSMS event has taken place. So throughout the mass range and throughout the retention time, we're able to acquire a vast number of MSMS spectrum so that we are able to confidently identify more lipid species. And if you look at the table on the right here, then you can see the number of MSMS spectra which were acquired between if you ran a standard QTOF injection, which is what has been labeled as TIMS off analysis, or a TIMS passive run where we have this methodology to increase our MSMS coverage. And this increases the number of precursors that can be targeted by more than 5-fold in this example for the SRM 1950 extract. And with this, we're then able to annotate the different lipids using either a rule-based annotation, which I'll go through how exactly this works, or by comparing to the lipid blast library, which now includes the CCS dimension to match against, as well as in silico MSMS. So in using this very fast method of acquiring MSMS, another advantage that we have is that we can increase the throughput. So these 3 different experiments here were conducted with a throughput of a 20-minute gradient, moving to a 10-minute gradient to a 5-minute gradient. And we analyzed how many different lipids could be annotated. And if you look at the orange bar, then at the 5-minute gradient, we were able to annotate 75% of the lipids that were observed within the 20-minute gradient. So we've increased the throughput by 4-fold, but the number of lipid annotations has not fallen by a significant amount. And with this, we can increase the throughput of our experiment so that we can run larger sample cohorts. And this is a nice example of two co-eluting lipids. So these structures shown here are just example structures for a P36(2) lipid and a PCO34(2) lipid. Now, in this chromatographic separation, they co-elute. And if we look at the 2 different masses, then you can see that they differ by just 36 millidalton. So if you were just running a standard QTOF experiment, then these 2 lipids would be isolated together in your quadrupole and fragmented together. But here we have this mobility separation, just shown on the y-axis. So when we look at the mobility of these 2 different species, then they differ significantly enough that they are fragmented separately. And you can see the fragment spectra from these 2 different lipids. And when we have the neutral loss, which is indicative of a P sample, and we have the PC head group, which is present at 184. And these 2 fragments are key fragments which form part of the rule-based lipid annotation, which enable all users to be able to assign these series of rules so that they can annotate different lipid classes based on these different neutral losses and head group fragments. So I mentioned that this workflow could be used for imaging as well as for LCMS, and this is a nice example. So in this example, this was where some lipids were extracted from spleen and then ran using hillock chromatography. And in this case, there's a near coelution of the PG and BMP lipid classes. Now, these 2 lipids are completely isomeric, so there's no way to separate them using mass alone. And you need an orthogonal type of separation, so either using long chromatography or different types of chromatography, or using ion mobility separation. And you can see from this, these mobility peaks that you're able to separate out these 2 isomeric lipids. And this can be translated onto an imaging experiment that we can now plot the spatial distribution of these different lipids on tissue. And we can confidently annotate where they are spatially, as we can look not only at the distribution of the mass to charge, but also the distribution of that CCS value. So from this, we can see the distribution of the BMPs versus the PG lipids. And we can also plot a number of other isobaric lipid species spatially. So for both MALDI and for electrospray, we're able to further validate different lipid classes by using the functionality called the Kendrick mass defect plot. So what we're doing here is we're looking at a 4-dimensional analysis in which we plot the number of double bonds, which we have, we know are within that lipid class, and we plot it against the chain length. So in this example, you can see these are all representing triglycerides, so TG lipids. And as you move vertically across this plot, then you can see that the number of carbons within the carbon chain increases by 2. And as we move down the diagonal lines, then the number of double bonds present within these TGs is changing. And you can use this, this view so that you can easily look for trends within your data and identify a large number of lipids of a specific class. And the colors within this plot, they show you the trend in retention time. So this fading of blue to red shows you that the retention time is increasing as you move down these lines. So with this, it's really easy for you to tell if you have a TG species with an incorrect retention time that doesn't follow these patterns, then you can really visually see this within the data set. Okay, so I've applied this workflow to an example data set, and this was for the analysis of C. elegans, and this was done with our collaboration partner, Michael Witting, who's based in the Helmholtz Institute in Munich. So this was a data set comprised of 3 different groups. So looking at the wild type C. elegans and at the control sample and also at the DAF2 mutant. So the DAF2 mutant is interesting as it's known to show changes in the aging mechanism. So it has an increased lifespan and it has an increased lipid content. So we ran this through our lipidomics pipeline to see if we could see a difference in the lipid composition between the DAF2 mutant and between the wild type. So the first aspect is using this passive acquisition. So this is the data from the C. elegans sample. So you can see the chromatogram at the top. And at the bottom, you can see these circles, which represent the number, which each represent a lipid precursor, which has been fragmented and then characterized based on the fragment spectrum. So this plot is a log plot. So this covers 4 orders of magnitude. So we're able to pick up very low abundant lipid species, including if you look here, then there's an area where there's very few lipid signals. But you can see we still get a very high MSMS coverage. And for in this experiment, more than 65% of the lipid features that were annotated contained MSMS spectra. Now, the workflow that we have uses our Metabolomics software, and this is able to analyze this, this data with the additional dimension of separation, so with this CCS value. And what we do is we have a single line within this feature table, and we collect all the different adducts which belong to a single lipid. And then we look at the CCS values between the different samples. So the different replicates of different biological or technical replicates in each of these samples. And in order to annotate the data, this was an example of a single spectrum for a PC lipid, where we can see this head group loss, but we can also see these backbone fragments, which are able to give us a deeper level of annotation. So we can see from these fragments that we have a PC 16,0, 18,0 lipids, and these rules are automatically applied within the software. And there's quite a nice feature that you can customize the database that you use to annotate these lipids. So you can pick from around 40 different lipid subclasses, And you can tell the software if you're interested in looking at lipids which have odd chains or only even chains. And you can also set the maximum and minimum number of double bonds that you would expect to see within that sample, knowing a little bit more about the biological relevance of the sample that you're running. And the nomenclature that's used is the latest review article from the Lipid Maps Consortium. So as well as using the rule-based annotation, we also match against CCS libraries. And we've been working with the team from Lipid Blast, who have integrated around 500,000 CCS values into the Lipid Blast library. So this plot to the right shows you each of the different lipid classes and how they exhibit a different CCS space. And you can see here, this is a screenshot within the software where you have the CCS value for each one of these lipids. And then you have a delta CCS, so a deviation between the measured CCS and between the CCS value from that Lipid Blast library. Included in the software is a statistical package. So for the C. elegans example, we can see that when we look at the scores and loadings plot, then we separate out these 3 different groups. So the blue is the QC, the green is the wild type, and the red is the DAF2 mutant. And we can see that we're able to separate those out. And then we're able to look at different lipids that could be significant that are differing between the 2 groups. So in this case, we can see there's a clear example of PC2525, which if we look at the box plot, we can see has a significantly different intensity between the 3 different groups. But within the chromatogram and within the mobilogram, we can see that we have reproducible both retention time and CCS values. And I can show you about how the lipid was annotated as PC2525. So first of all, a combination of positive and negative mode data was used. So in the negative mode data, we see more information about the sidechain fragments. And in the positive mode data, we get the more information about the head group. So by combining both the positive and the negative data set, then we're able to see more fragments and give a more confident annotation that this is the PC2525 lipid. And then as well as using MSMS, we can use the CCS value. So in this case, the value was within the Lipid Blast library, but if you have a more unusual lipid structure that is not part of a library, then you can use an in silico CCS prediction, which is also built within the software. So with CCS prediction, what you would typically do is you would take the lipid structure and feed it into a machine learning approach so that you are able to look at a predicted CCS value. But a lot of the times when you look at lipids, you don't know a full structure. So you are able to annotate the lipid to a species level or to a molecular species level. And so what we've developed is a new CCS prediction where you no longer rely on the structure, but instead you rely on this shorthand notation. So you can tell the software the number of carbon atoms, the number of double bond equivalents, and from that, you can read out the CCS value. So we call this a hyperplane model, where you can use this hyperplane to get a prediction of the CCS, even if you only have the molecular species or species level. So in this case, we did this for this PC2525 lipid, and you can see here the CCS deviation that was measured out between the sodium and the protonated species. So this is typically less than 2%. And you can give, you can use this to validate that the structure of the lipid species is the correct one, and then investigate the biological relevance of this lipid in more detail by looking at different pathway mapping. So that brings me to the end of the tutorial. and the demonstration of what is possible within our software. I'd like to thank the organizers for the opportunity to present this here and invite you to ask any questions. Thank you.
Great, thank you very much. Let's see, we do have a question in the chat from Siju. Someone in the morning asked if you can calculate FDR for a lipid annotation. Can you share your thoughts?
We don't have FDR in our software, but we get increasingly asked that question. And there's a lot of different discussion on what approach to be taken. And I'd really like to see within the next 1 to 2 years, it starting to be implemented into different software packages. So I think with the Lipid Maps Consortium, and I know there's a lot of work with metabolomics standardization, then hopefully that's an area that we can work towards and agree on a way to actually calculate FDR, but there's certainly a lot of discussion around it. So I'd be happy to hear if anyone has any strong opinions as to the best way to do it.
Does anyone on this Zoom want to comment further? You can just unmute yourself and speak up. Could be an interesting question to ask tomorrow afternoon speakers, both of whom have really been involved in, database development. See what they would have to say.
Well, obviously, there's a lot of more work needed to be done. In terms of specifically the position of double bonds. That is not solved, at least not easily. There are, of course, approaches using ozonation and so on, right? There's some new instruments on the market that can assist here. But, currently what you see is like 20 to 5, like just was what Lucy just showed. And you can assume that this is the classic EPA fatty acid. But it, in other instances, might be something else, right? So also for odd chain fatty acids, for hydroxy fatty acids, where is the oxidation? Where are the, that's the next step in disambiguation of structures of lipids. Yeah. So there's always one more thing to do.
Especially in metabolomics. Siju, you had a question in the chat, but I wonder if, as Lucy's talk went along, she already answered it. Do you want to follow up on that?
Yeah, very good talk, Dr. Wu. So just a quick question. You mentioned the predicted CCS values. I'm just curious how good it is compared, to the measured real CCS values on the ion mobility instruments. So
we typically see a deviation of, I say less than 2%. Majority of the time it is less than 1%. And that's the same if we look at reproducibility across different platforms. So for the CCS value, we've compared it between different timsTOFs and different drift tube platforms. And for that, we'll typically see around a 1% deviation. And then if we look at predicted values, then it's typically under 2%.
Oh, that's pretty good, actually.
It depends on the training set. So we have 2 different models for our prediction. And we have one that only uses lipid CCS values for the prediction model. And then we have a more general metabolomics CCS prediction. And that uses a combination of different compound classes. So different metabolomics, different drug metabolites, different lipids. And for that one, you would expect a larger error. For example, if you were looking at a large lipid and that wasn't covered by the training set data. So instead, we prefer to have 2 different models and keep all of the lipidomics data into a single model, and then that gives you better accuracy.
Thank you.
Great. We have another question from Sergei Giro. He says, the increase in the number of acquired MS2 spectra with passive is quite overwhelming. However, annotations increase more moderately, which speaks for some redundancy.
Mhm.
Do you have a comment about effective acquisition strategies to mitigate this?
So what I showed in that table was there were a couple of columns. There was the increase in the total number of MSMS spectrum and the increase in the number of precursors targeted. So the largest increase is in the total number of MSMS spectra, which you would expect because it's 10 times faster, and you can see this from the values. So we want to target some low-level precursors more than once. And this is why when you look at the number of precursors targeted, the number drops from 25,000 to 18,000, because the way the passive scheduler works is to fragment low-level lipids multiple times to get better signal to noise and a better chance of annotating that lipid. Now for the actual lipid annotations, yeah, I agree, it's a bit lower. I'd like to see it much higher. For the rule-based annotation, that the number of annotations is restricted by how many lipid classes that we have in the model, which at the moment we have around 40 lipid classes, but there are rules that are continuously being published for new lipid classes. So as those are published, we can enable that rule-based annotation to grow to cover more lipid classes. You can kind of see this in the lipid blast ID. So in lipid blast, that covers more, I think that's already around 101 different lipid subclasses. This is why you have a higher number of annotation, and why this combined annotation here gives you some additional ones, but you will have low overlap between the lipid blast annotation and between the the rule-based annotation. So hopefully that explains those numbers in a little bit more detail. And I think the main thing that we need to do there is keep increasing these rule-based approaches or library-based approaches in the case of lipid blasts, so that we can cover more molecular space.
Yeah. We have going back to CCS, we have another question from Nide. Does the structure of lipids make the CCS more predictable than, say, for peptides?
For the CCS values, easier for lipids, yes, because they have a more well-defined structure. So you can imagine that, I don't have a slide in here, but as you increase the number of CH2 groups on the backbone, then you get a very reproducible and linear addition of the CCS value. And same for if you switch different between different lipid classes. So the head group itself will add a certain amount to the CCS value, whereas for small molecules, there's a much more diverse structural space. And for peptides, it should be similar to lipids in that you have these well-defined building blocks that you can use for CCS prediction. And one of the main benefits of for peptides is that there are huge databases already. So databases of more than 1 million CCS values, which can be used for CCS prediction models and can be used for training set data. So I think for peptides and lipids, we're in a similar position, and for metabolomics or small molecules in general, then there's a bit more work that needs to be done to get more data.
Mm-hmm. And speaking of peptides, I have a question. So it's peptides, not lipids, but I have a question about use of isobaric tags with the timTOF Flex. Mm-hmm. So I was told that the timTOF Flex has a bit worse mass accuracy than the Orbitrap. Mm-hmm. So that if you're doing TMT tagging, there's some TMT tags you can't use on the timTOF Flex that you could use on the Orbitrap. Mm-hmm. That's correct?
Yeah, okay. So we typically do TMT 6-plex and not higher, because that's mm-hmm. The mass difference is sufficient to be resolved on the platform. I think that you can also use the 16-plex, but you don't take, it's not a 16-plex experiment. You resolve, I think about half of
you leave out a few of the tags.
Yeah.
Yeah, great, thank you. I think that's all the questions we have in the chat. So thank you very much, Dr. Woods. Sisha, do you have any follow-up general announcements or comments?
I don't know. I think there is one last question from Oliver, maybe to Dr. Wu.
Oh, yeah. Okay,
Yeah. So I will just read the question.
go
So
ahead.
Metabolomics community tries to come up with means to calculate it. Confidence meaning the likelihood that an annotation could be wrong. Calculate FDR values.
Mhm. So was that a question or a comment?
Is a question. I think, can you calculate FDR values? I think. I don't know. Maybe he asked you. Oliver, you wanna, or is it just a comment?
Well, I mean, you know, the idea is that you have 4 different parameters. You have LC retention time,
Yeah.
you have the accurate mass, you have an MS spectrum, and you have a CCS value. Each comes with subtle windows of accuracy, right, in the measurement.
Mhm.
Can you combine these scores? And have you tried that? How close then those would be to an alternative explanation?
Mhm. It's not something that we've tried, but it's something that we could discuss.
Okay. Yeah, I'm just saying that, you know, this is the obvious next step, right? Not just naming a compound, but also saying, well, I'm 99.999% sure.
Mhm.
Maybe next time I'm just 95.7% sure, or so,
Mhm.
right? Because it could be, you know, there's an overlap in CCS and in whatnot, you know, to an alternative explanation of my data.
Mhm. Yes, good point.
Yeah, like a score like a protein, you know, for protein identification, you have a score, like a mascot score, something like that.
Mhm.
Good.
Yeah, I know it's come up in discussion a lot after the recent publication. So at the moment, the way that we do it is not numerically. We characterize each of the attributes separately. So with accurate mass, with retention time, with isotopic pattern, MS fit, and CCS prediction. And we have a score for each of them, but we haven't as yet combined it into a combined score. But it's something that you're right would be the next step.
Well, the trouble is you don't know the universe of everything else that can collude. That's the problem, right? So if it's obvious, it makes a difference if you have 100 lipid classes or 40 that you consider, right? So you can only consider the space that you do consider. So if you, you know, so if you consider 40 lipid classes, it may be fine. If you all of a sudden consider 100 lipid classes, then all of a sudden there might be new events popping up, coevolutions or possibilities.
Okay.
Great. Well, thank you very much. And I'd like to, I think we should thank all the speakers from the entire day for a great series of presentations. So.
Thank you.